As I already mentioned, I want to talk about eBPF, XDP, what it is, and what are some recent developments in Linux kernel community. To start off, what is BPF? Probably everybody of you has used TCP dump in one way or another. If you enter some filter in TCP dump, that filter gets compiled down into some bytecode. This bytecode is called BPF. This is done by libpcap and then pushed into the kernel in AF packet. And that is already existent for a very long time. And nowadays we call this classic BPF or cBPF, and this got extended heavily, probably like 1 or 2 years ago in the kernel, into something that is called eBPF. And eBPF is an efficient, generic in-kernel bytecode engine. It is used in many different subsystems in the kernel right now. There are probably like three major areas, which is networking, tracing, and also sandboxing or security. Regarding tracing and sandboxing, so tracing, for example, you have like perf, where you can attach BPF programs to trace points, k-probes, things like that, and then every time an event triggers, an eBPF program runs, and then you can analyze different things in the kernel. You can read kernel memory and so on and so forth. For sandboxing, probably the most popular or most prominent user is the Chrome web browser, where it uses seccomp BPF to filter on system calls, to whitelist system calls and so on. So this is quite flexible. That seccomp BPF is not eBPF yet. It's cBPF, so still this classic BPF that is pushed down into the kernel. And networking, which is what we want to talk about here, there are various things. For example, in sockets, you have socket filters with AF packet. What I already mentioned, then you have various DMUX facilities. For example, SO reuse port, when you have multiple sockets that are in a group that can reuse a specific port, then you can have an eBPF program that makes the decision to what port that connection is going to be. You also have for AF packet, for example, fan out, where you have multiple AF packet sockets, and then the traffic can get load balanced like that to one of those sockets participating in that group. And then you have XDP and TC. So I will start with the facility that we have in TC. This is called CLS BPF or BPF classifier. It's called like this, classifier for historical reasons, but it can do way more than just classification. So it's a flexible, programmable packet processor in the TC subsystem. You can attach that. You can attach an eBPF program there on the ingress or egress path of the kernel data path of networking device, and yeah, and then we also have XDP, which got recently introduced into the kernel. This is also programmable but high performance in kernel packet processor. That is attachable to drivers that support it, and on the ingress side of the driver. I will talk a bit more about that later. I think both things, they are complementary to each other in the sense that CLS BPF can be attached to all networking devices, also virtual ones like Weave devices for different networking namespaces, and it can be attached on ingress and egress, and XDP is currently on ingress. And for CLS BPF, you have a socket buffer, which is the networking representation, the kernel representation of a network packet. As you have that as an input into the BPF program, where it works with that data, and you have a bit more richer context with that. But both are complementary to each other and quite flexible. So first, before I dive into the details of both subsystems, I want to present shortly about the eBPF architecture. It consists of 11 64-bit registers. You also have 32-bit sub-registers there. You have a stack that is limited. It's currently 512 bytes on the kernel stack. Implicitly program counter, of course. the instructions, they're fixed size, 64-bit wide, and you can have maximum of 4069 instructions per program, which doesn't seem much, but you can still do quite a lot and quite also complex things with it. Compared to the cBPF that we know from TCP dump, like what I mentioned earlier, there are various new instructions. Of course, you have the whole 64-bit range of instructions for ALU operations, for example, because the cBPF was only on 32-bit, and you have things like you have a call in instructions where you can call into a helper function, what I will explain that later. So there's various new instructions. Some of the core components of the architecture is that you have read and write access to the input context. The input context, as I mentioned, for example, in TC is a socket buffer. In XDP, it's like a small representation where you can access the like the network packet for the XDP representation. Then you have a helper function concept, which means that the kernel exposes a fixed defined set of helpers or like functions that the BPF program can call into. So it cannot call arbitrary kernel memory, but just a fixed set. Then there are maps. Maps are efficient key value data structures that can be shared arbitrarily, which means one or multiple eBPF programs can access that map, or user space can access and read or update data from it at the same time. So then there are tail calls. Tail calls, the concept where one BPF program can call another BPF program. So you don't have this fixed limitation of 4069 instructions per program, but you can also go beyond that. And this is quite useful. It reuses the same stack frame, so it's also quite fast. Then there's a concept of object pinning, which means that from the user space perspective, programs and maps, they're accessed through file descriptors. And once you load your eBPF program into the kernel, for example via TC, then this file descriptor your file descriptor is basically unavailable for other programs to use. And to share maps with also other applications, you can pin them in a pseudo file system as a node there, and then those other programs that can retrieve it and also work on this map to update or read data. Then in the kernel, there's a cBPF to eBPF translator, which means that whenever you load your classic TCP dump filter in the kernel, that gets transparently translated to eBPF and only runs on eBPF. And the nice thing about eBPF is that from user space side, LVM has an eBPF backend, which means that you can write a C-like program, and LVM translates that into an object file, which has eBPF instructions that can then be loaded into the kernel. And last but not least, there's not only an eBPF interpreter in the kernel, but also a just-in-time compiler. So whenever you load a program and the just-in-time compiler is enabled, then this gets mapped directly to native opcode, so you can run with native performance. All of that is managed through the BPF system call. So it's like a stable API, and also your programs, when you implement them, they're basically stable. So once your kernel supports that, it's like a guarantee that newer kernels will also support that in the future, unlike, for example, kernel module where internals can always change. So to give you some more details regarding TC, TC, you can basically attach this CLS BPF to QDisk, and there's like a QDisk which is called chat CLS act, which is just a pseudo QDisk similar to the Ingress QDisk in the kernel, and this is only there for the purpose of attaching classifiers and actions, if you're familiar with TC. in that case, what we want to attach is, of course, CLS BPF. There are like two central hooks where this shared CLS ACT QDISC can attach to, which is the ingress and the egress hook. So they are basically like really central places where every packet has to go through from RX and TX side. CLS BPF, it runs eBPF. Historically, it also supports cBPF. So both flavors, and you can atomically update your programs during runtime, which is really useful. Either the root program that is attached to the CLS BPF classifier itself, or those tail calls where one program calls into another, they can also atomically get updated during runtime without restarting your networking interface, things like that. And CLS BPF has a fast path, which means that historically TC had classifiers and actions, what I mentioned, and classifier, once it's done classifying, can then call into a chain of actions, and all of that is pretty inefficient. And eBPF can do everything contained in itself anyway, so therefore this CLS BPF has a so-called direct action mode, where eBPF can classify a mango, perform various actions on the SKB, on the socket buffer that is as an input, and then just return a verdict and then be done with it. So it doesn't call into a chain of actions or whatever. Everything is done in the eBPF program itself. And there's also an offload interface available. For example, the Netronome NFP driver, if you have such a Netronome SmartNIC, can offload eBPF programs, which means that whenever you load your program to CLS BPF and have such a card, then it gets translated into a native code that is supported for the instruction set on the NFP driver. So a typical workflow would be you write your C program, you compile it with LVM, it gets translated into ELF instructions, into eBPF instructions. They are contained in an object file. TC, in that case, can read that object file and load those instructions into the kernel. In the kernel they get verified, which means that verifier makes sure that the instructions cannot crash the kernel, it cannot create infinite loops, things like that. Then it gets just-in-time compiled, then this is pushed down into CLS BPF classifier, and then eventually gets offloaded. So that's like typical workflow for that. And XDP, on the other hand, this was introduced probably 1 year ago into the kernel. The objectives there is that it's really tailored for high performance packet processing. So what it does is it runs an eBPF program at the very earliest point in the driver. So this is earlier, so even before you allocated an SKP metadata structure. This is also one of the overheads the kernel have for doing high performance packet processing with small packets in particular. And the nice thing is that this kind of framework works in concert with the kernel, which means it uses the same security model. You don't have your NIC representation or your driver in user space and have it exposed there, but it still stays in the kernel. There's no out-of-tree module needed for accessing that. And the packet itself, it also stays in the kernel, which means you don't have to cross boundaries when you want to get it out or when you want to push it back into the kernel, which is, for example, nice if you want to work with containers. For example, one of the use cases could be that you're implementing a firewalling application, and there you can already filter packets out at the very earliest possible point on your NIC, and then from there, part of those packets that can get further passed to the kernel stack and then into some of the containers. Other use cases include load balancing. For example, direct error return load balancing is currently possible with that. And mangling and forwarding or denial of service measures. Monitoring is also possible, so there's currently an interface where you can push packets to user space for sampling or monitoring from XDP side. And you have various verdicts similar to TC, which means either you can drop packets, pass them further onto the kernel stack, or transmit them out again. And there are currently a number of drivers that support that. For example, Mellanox drivers, MLX4 and MLX5. Then we have the Metronome driver again, and QLogic. There's recently RedIONet support that has been merged, and Intel i40e was posted to the NetDev list, so it will be merged soon, and as well BNXT. The drivers, or at least some of them, currently depending on the implementation, but that will change in future, that all of them will support that, most likely. Allow also for atomic updates. So once you have your XDP program loaded and you want to update it with a new version, this can happen without disruption of any traffic. And also XDP has an offloading interface. And again, also Metronome has support for that. So once you load your XDP program, Metronome can offload that with a couple of limitations currently, but it's already a good way forward. And the workflow here, similar to what I mentioned earlier, you have your C program, you have LVM, and this time IP, so IP link command can be used as a loader for pushing the BPF sequence down to the kernel. And some of those features, I mentioned there are maps which are efficient key value stores. You can, from a BPF program, look up, update, or delete elements. Currently there are a couple of flavors, which are array maps, hash tables, least recently used maps, and longest prefix match, which has been merged not too long ago. They are all available for both types. And for the array, hash, and LRU, you also have per CPU variants, and there's also a possibility to pre-allocate the whole memory, so you have a pool, and you don't have to allocate your elements through the normal kernel allocation facilities. Then there are also specialized maps, which means they cannot be used like those generic maps, but they're rather used with BPF helpers. For example, the program array map, which is used for tail calls, where you can push file descriptors into this specific map, and then you can jump into that through that. There's direct packet access, which means, and it is supported in both cases, CLS, BPF, and XDP. Direct packet read and write means that in the past, CLS, BPF had to use helper functions where you pass in a stack buffer and then it gets filled with the offset, the number of bytes you want to read. But direct packet read and write means you can, for example, just cast your header directly without having to go through helper. So it's a performance optimization there. You have a couple of additional metadata. For example, in the socket buffer case on CLS BPF, you can use SKB mark, for example. There are various other things there, but so it can work with other facilities from the kernel as well. Regarding packet forwarding, so CLS BPF, as I mentioned, it can forward. So it can forward packets to any networking device, including virtual ones. So when you push that into container over Reef, for example, you can push it out to the same port, or it can loop it back to the ORX path. For XDP, it's currently still limited. So in XDP case, you can only push it out to the same port it came in. But there's work in progress to also support multi-port TX or TX through a different net device that also supports XDP. That will come in the future, but currently to the same port, it's still useful because, for example, when you have the load balancing use case with direct serial return, your node that runs, or your load balancer that would run XDP gets the packet in and rewrites various parts and push it out again, but the reply packets, since it's direct serial return, go a different path, so it's still very useful to do that. Then some miscellaneous things. You can do encapsulation. So there's VXLAN, Geneve, GRE, IP encapsulation available for CLS BPF. In XDP, you're way more flexible actually. You can do any kind of encapsulation you want because at that early point in time, the kernel doesn't know anything about the packet that is coming in yet. And so you're not limited by the current internal details from the socket buffer itself. Then there's also event notification, which is a really useful feature. What it does, you can have your own custom structs in the eBPF program, and then push that to a high-performance per-CPU memory-mapped ring buffer to user space. That can be some specific metadata or data and packet and the packet data itself, up to the full packet. So that is useful if you have some management daemons that then listen on certain events and update later on map data or programs for tail calls and so on. You have checksum mangling, you have C-group support, and various other things. IP Route 2 as a loader, I already mentioned it, that it has, it can push down the eBPF bytecode into the kernel. Just to give you an example how it looks, so for example in TC case you set up the QDisk first, then you can set up the filter, and then you here define whether an ingress or egress site you want to hook that BPF program to, and then you define the object itself, and then the object can have various sections which contain the program code, the actual program code. And an XDP workflow, it's currently where you can say, I want to load the program via IP link, and then as well specify the object, and then it gets pushed down. They have a common shared library as the loader backend. So it doesn't necessarily have to be IP Route 2. You can also have other loaders if you program them yourself, or other libraries that support it. So it's just one flavor where you can do that. Then regarding just-in-time compilers, there's x86 support, ARM64, PowerPC, and S390X. So they all have eBPF offloads. PowerPC got recently merged, which is nice, and the same for the NFP driver, which also implements a just-in-time compiler for the NFP-specific instruction set for the networking offload. There are various measures against for hardening those jittered programs. I'm not going too much into detail here. And there are other recent improvements. For example, LVM's eBPF backend recently got TWARF support, which means you can annotate your code with the actual, your generated object code with the actual source code that you have, and it's definitely an improvement for debugging. There are various verifier improvements that can recognize the LVM generated code a little bit better in the kernel, so it accepts those programs as well. And trace points have recently been merged, and so on. So a couple of next steps. So definitely there still have to be improvements from the verification side in terms of logging, or provide more helpful user messages, for example. Then in terms of search pruning, so that the verifier can more aggressively so that the verifier doesn't have to do too much work to verify each possible path of the program. And then there has to be better XDP driver support in future, but that will come over time. And yeah, so those are some examples of next steps regarding code. If you want to look at some code and how the BPF parts are written there, I can recommend you to go to github.com/Cilium, which is a project which implements basically BPF and XDP for containers. There will be a talk afterwards for that, and everything else on the kernel and IP route 2 side is merged upstream. And for further information, you can also look at the NetDev conference papers that are there, or the kernel documentation, and so on. Are there any questions? All right.
There's an asymmetry there between the features supported between CLS and XDP.
Right.
Do you expect convergence over time, or I know there are two different levels in the stack, would you expect them to converge over time?
Right. I don't expect to converge all of that, because I mean those are like two different layers of the stack. And for some situations or use cases, one thing might be better than the other. So it's not like it will be exactly the same or something, right? So as I mentioned earlier, they are complementary to each other. So yeah. All right.
Is it possible to modify packets in XDP based on states, like when you want to keep different IP before NAT or something like this?
Right. So you definitely can. Okay. I should repeat the question. Is it possible to modify packets based on state, for example, for nutting? And yeah. So it's definitely possible. So state you can hold basically in BPF maps. That's what they are there for. And you can modify. So as I mentioned, there's direct read, direct write possibilities. So yeah. Cilium, for example, does that.
Does it also work when it's offloaded to the hardware?
So I'm currently not quite aware what features metronomes support, but I think they should be able to write as well. Okay, but the one limitation for the metronome hardware is that they do not yet support BPF maps, but that will come in future. So there's work in progress from metronome side. I don't work for them, but just to tell you what I know. Okay.
So one of the next steps of XDP is to be able to forward to any port. What is the most difficult in this task?
I think the most difficult task is so one of the challenges in XDP is that you forward this to a different port, and what is the most difficult task there, right? Is that you have you need to have so there's currently work regarding having a page pool allocator, which means that if you want to forward that to a different NIC even, they have to have some common understanding on how to transfer the packet from this side to another, right? Without copying, for example. So you need to have like a common shared page pool construct that you can just transfer those pages to the other one, so that they can TX that. Yeah, so there's still, I think, quite some work there to get that supported. Yeah.
What's the looking logic? Because right now the execution has to be per flow.
The what? The locking logic?
Yes. Is it for maps? Sharing maps between.
For maps. So what about the locking logic for maps? And yeah, so for example, array maps. On array maps, whether you have it per CPU or not per CPU, you're basically on your own, which means that the program has to be written in a way that it doesn't have race conditions. So you have some instructions, for example, atomic add, where you can use to increment counters on that side. For the hash tables, you have basically the update helper call, which atomically replaces one hash table map element with another. And so yeah, so there are various. It is dependent on the map certainly, and but there are various performance improvements to be done still. All right. You can also grab me in the hallway if there are further questions. So thank you very much.